This is section 13.7, part B. So, as I've noted here, if we're going to do an integral start to finish with a substitution method, it's going to take us a little bit more creativity and oftentimes a little trial and error to hit upon a good transformation that works really well for any particular problem. There are two tips that I can give you to help choose transformations if they're not given to you. Some of your practice problems, they'll just be given. First of all, try to use a transformation that makes the integrand simpler. If you can't integrate what you have, think about what you might be able to set u and v equal to that would make that integrand a lot easier to deal with. Secondly, try using a transformation that makes the region of integration simpler. We'll see examples of both of those things. In example 2, you can see already that the integrand itself is not an easy integrand to work with. I couldn't do just a standard u substitution and have this work out well for either x or y. So I think I'm going to concentrate on making my integrand simpler here. Under my radical, I have two factors. If I could make the first factor u and the second factor v, then I'd just have the square root of uv, which is a whole lot easier to integrate than what I have now. So I'm going to try that. I'm going to choose to let u equal 2x, and then I'll let v equal y minus 2x. So making the integrand simpler. Because I chose for the u and the v, I'm going to have to solve for the x and the y before I can do my Jacobian. So let's do that. Solving for x is pretty straightforward. X is just going to be 1/2 u. And since I can substitute u in for the 2x here, v is going to be y minus u. Actually, let me do it down here. V equals y minus u. So y then would equal v plus u, like so. So just manipulating these two equations until you can get an x equals and a y equals. That then allows me to do my Jacobian, which would be the magnitude of, or the determinant of, x sub u, x sub v, y sub u, y sub v. And in this case, x sub u is 1/2, and x with respect to v would just be 0. Y sub u is 1, and y sub v is also 1. One half times 1 is 1/2, minus 1 times 0 is 0. So the value of the Jacobian in this case is just 1/2. All right, so that's half the battle. The second half of the battle is to figure out what the r is going to turn into. What region S will I actually be using? So to figure out S, the region of integration, I'm going to start by looking at r itself, and then we'll apply these transformations and see what we get. So here's r. It's the parallelogram with vertices 0, 0, 0, 1, 2, 4, and 2, 5. So this parallelogram was the original region R. I'm going to transform that into a region S that can be used in my new integral. In order to do that, I'm going to set up a little chart for myself. I want to change all of these x and y values, so these are x and y values, into u and v values. Keeping in mind that u is 2x and v is y minus 2x. So I'll begin with 0, 0, my origin. And if I transform that, 2x, 2 times 0 is still 0. And then y minus 2x, 0 minus 0 is still 0. So the origin appears to have stayed exactly the way it was in my region S. So this is now my UV plane. 0, 0 is still 0, 0. All right, let's do another one. Let's go ahead and do the point. Let's see, is it 0, 0? Let's go this way. Let's do this one, 2, 4. Again, just plugging in x equals 2 and y equals 4. 2x, 2 times 2 is 4. Y is 4, minus 4 is 0. So I'm now at 4, 0. That line on the parallelogram has become that line segment in the UV plane. Next, I'm going to go up here to 2, 5. And let's see, u is 2x, so that's still 4. And then 5 minus the 4 would be 1. So 4, 1 is my new point in the UV plane. Again, this line segment here became that line segment in the UV plane. All right, we have one more point to deal with, and that's this one over here. It was the point 0, 1. Let's see, 2 times 0 is still 0, and 1 minus 0 is still 1. So that point is still 0, 1. And that line segment in R just became this line segment in S. Finally, I wanted to connect the 0, 1 to the 0, 0, and those 2 points didn't change. So this last line segment coming down here is still the same over here. All right, so here's our new region of integration. And even though the original region of integration wasn't bad, right, you wouldn't have had too much trouble setting up x and y limits of integration for this. Notice this is even better. Everything's going to be constant. It's just a nice rectangular region. So we've actually accomplished both things. We're going to have made our integrand simpler, but we've also made our region a bit simpler as well. All right, so we're ready to put this all together. We need the double integral of our new function. Again, the square root is now going to be the square root of u times v. Times the absolute value of the Jacobian. Our Jacobian we calculated was 1/2. And let's just go ahead and do this dv du. It doesn't really matter, but I'm going to think vertical rectangles. And since v is my vertical variable, that means I'm doing dv first. So v goes from 0 to 1, and u goes from 0 to 4. All right, that looks a lot better than it did in the x and the y iteration, so I think we're going to be okay here. I'm going to pull that 1/2 out. And I'm going to think of this as u to the 1/2, v to the 1/2. So the integral dv, u to the 1/2 is still a constant multiplier, and that's going to become v to the 3/2. Dividing by that 3/2 is multiplying by 2/3. So I'm going to just pull that 2/3 right out here. And that goes from v equals 0 to v equals 1. Let's see, 2's will cancel there, so I'll have a 1/3. Plugging in a v equals 1 is just going to make that 1 times u to the 1/2. And plugging in a v equals 0 is 0. And so I have a nice simple integral to finish that off with. When I did that on my calculator, I got, including the 1/3, I got 16/9. All right, let's try another one. In example 3, we're looking for the integral of xy dA. And then we're given these boundaries for the region R. In this case, the integrand itself is not difficult to do, right? The integrand's no big deal. Doesn't require a change of variables at that stage. But let's look at the region and see if there's some region based on, or some reason based on R that's going to make me want to do a change of variables. All right, we've got y is equal to 2x plus 3. We've got y equals 2x plus 1, so a parallel line down here with a y-intercept of 1. And then we've got y equals 5 minus x. And then y equals 2 minus x. So this is our region R, in between all of those, the region bounded by them. So this is R, and we are in the xy plane. Here's what I hate about that region. If I were going to do my integral with x's and y's, I believe that I would need at least 3 double integrals to do this. I'd have to imagine breaking it up here between those 2 lines, again there between these 2 lines, and then over here between those 2. So there would be 3 distinct pieces that I would have to do to set up this integral. And it's exactly the same if I go horizontally. So in order to avoid having to do 3 double integrals, I'm going to say, could I just change my variables, do a transformation, and maybe get a nicer region? This happens really often when you have parallel lines. Here's what I'm going to do. I'm going to take a look at those 2 equations, and I'm going to say, if I were to subtract the 2x, I would have negative 2x plus y equals 3, and down here I would have negative 2x plus y equals 1. What that suggests to me is maybe one of my new variables should be equal to negative 2x plus y, because then that new variable could just go from 1 to 3 and be really, really nice. So let's do that. Let's let u equal negative 2x plus y. That way I go from u equals 3 to u equals 1. I can do something very similar with these 2 equations. If I bring the x over, I would have x plus y equals 5. And down here, I'd have x plus y equals 2. Since the left-hand side is the same in both equations, I'm going to let my other variable, my v, be the x plus y. That way I've got v equals 5 and v equals 2. That, of course, is a much nicer region to integrate over. In fact, if I sneak it right in here, this is now my region S. U goes from 1 to 3, and v goes from 2 to 5. This is my u-axis, that's my v-axis. So I just get this beautiful rectangle. 2 to 5 on the v direction, 1 to 3 in the u direction. That certainly is going to be a much, much easier region to integrate over than the original R was. So I'm happy with the region. In fact, I even know the limits of integration already for u and v. What I need to do now is figure out my transformation equations so I can get that Jacobian that I need to do the integral. So here's the transformation issue. We have u equals negative 2x plus y, and we have v equals x plus y. I need to get those equations in the form x equals and y equals so I can do their derivatives for my Jacobian. So what I'm going to do is I'm going to use an elimination method this time. I'm actually going to keep the u the way it is. And I'm going to multiply the v by 2. So 2v equals 2x plus 2y. That eliminates the x's. So I have u plus 2v equals 3y. And dividing by 3, I have 1/3 u plus 2/3 v equals y. So there's my y equation. If I now do something kind of similar, I can either eliminate again, or I think I'm just going to substitute. If I go ahead and substitute the y into this bottom equation, so I have v equals x plus, I'll replace that y with a 1/3 u plus 2/3 v. I can move everything to the left-hand side. So I'd have a negative 1/3 u, and v minus 2/3 v would be a positive 1/3 v. And that's equal to x. So I now have these two equations for my transformation. An x equals equation and a y equals equation. That means my Jacobian, which is x sub u, x sub v, y sub u, y sub v, is going to be x sub u, negative 1/3, x sub v, positive 1/3, and y sub u, positive 1/3, y sub v, positive 2/3, giving me, multiplying these is going to give me negative 2/9. Subtract, multiplying those gives me 1/9. So I get negative 3/9 or negative 1/3 for my Jacobian. All right, I think we're finally ready to actually get our integral done. So we have the double integral. First of all, the integrand way back up here was x times y. I'll have to write that in terms of u and v. So let's see, it's x, negative 1/3 u plus 1/3 v, times y, 1/3 u plus 2/3 v. And it doesn't really matter. I'm just going to go ahead and I'm going to assume vertical rectangle, so I'm going to go dv du. V went from 2 to 5, and u from 1 to 3. All right, we definitely made our integrand a little bit uglier, but it's just polynomials. They're not too bad to deal with. Our limits of integration, however, are really, really nice, and we only had to set up one double integral. Oh, you know what, though? I did forget something. I forgot the Jacobian. This has to get multiplied by the absolute value of the Jacobian. So the absolute value of negative a third. Sorry about that. All right, so we've got some work to do. First thing I'm going to have to do is multiply out that entire integrand, unfortunately. I'm going to pull, that's really a positive 1/3. I'm going to pull that out. And we're going to go ahead and multiply here. Negative 1/9 u squared. Outers would be a negative 2/9 uv. Inners would be a positive 1/9 uv. And the last would be a positive 2/9 v squared. All right. Let's see. I could go ahead and take these two terms and put them together. That's really just a negative 1/9 uv. And so, actually, you know what? I'm gonna write this out one more time. I'm gonna pull out the denominator of 9 on all the terms. So I'm gonna pull out a factor of 1/9. And that'll just make that a negative u squared, a negative uv, and a positive 2v squared. That makes it just a little bit prettier to have to integrate. So I've got 1/27. And then integrating, oops, I lost my du here. Integrating dv first, however, I'll have a negative u squared v minus 1/2 u v squared plus 2/3 v cubed. And we go from v equals 2 to v equals 5. So plugging in v equals 5, I'll have a negative 5u squared, a minus, that'll be a 25 over 2 u, and then a plus 125 times 2 is 250 over 3. Subtract. Plugging in the v equals 2, a negative 2u squared, minus v squared is 4, so half of 4 would be 2u, plus v cubed is 8 times 2 is 16/3. And of course that still has to be integrated du. Up to you, you can play around with the algebra a little bit first, or you can just plug it in that way in your calculator. When all was said and done, and I did the entire integral, including the multiplication by 1/27, I ended up with 88 over 27 for the final value of this integral. All right, we will come back for the last example in one more video for this section.